Locked inside permanently shadowed craters at the moon's south pole, there is water ice. Confirmed. Billions of tons of it. And it changes everything. We thought we were going back to plant a flag. We were wrong. The real mission is fuel, minerals, territory, and a launch pad to the entire solar system. We'll cover why every space agency on Earth is suddenly racing to the same spot. What's hiding in craters that haven't seen light in over 1 billion years, and why the moon might become the most contested piece of real estate humanity has ever fought over. If this excites you, subscribe. You won't want to miss what's coming. Strap in, we begin. 52 years ago, we left the moon and never went back. Eugene Cernan climbed into the lunar module in December of 1972, looked out at the grey hills one last time, and sealed the hatch. He was the last human being to stand on another world. And for half a century, that is where the story stopped. That fact should bother you more than it does. We had the technology, we had the engineers, we had 12 men who had already made the trip and come home alive. And yet, after 6 successful landings, America looked at the moon, looked at the cost, looked at a war in Southeast Asia and a fracturing economy, and said, enough. The Apollo program burned through roughly $150 billion in today's money. At its peak, it employed 400,000 people. It was the largest coordinated scientific effort in human history. And then Congress cut the funding, 3 planned missions were cancelled, and the Saturn V rockets sat in museums while the people who knew how to fly them retired or passed away. Here is what makes that decision stranger. The longer you sit with it, we stopped going precisely when we were getting good at it. The early Apollo missions were survival exercises. By the end, astronauts were driving rovers miles across the surface, collecting samples from multiple geological sites, and conducting experiments that scientists are still analyzing today. The last 3 missions, 15, 16, and 17, were genuine scientific expeditions, and we cancelled the next 3 before they ever launched. Why? The short answer is politics and money. The long answer takes the rest of this video to explain, because the decision to stop going shaped everything that happened in space for the next 50 years. The Soviet Union lost the moon race and pivoted to space stations. America built the space shuttle, which was brilliant and expensive and could only reach low Earth orbit. Decades passed. The International Space Station consumed the budgets and attention of every major space agency. The moon sat there, 240,000 miles away, waiting. Something changed in the early 2000s. Scientists started getting serious results back from orbital probes, mapping the lunar surface. Instruments detected hydrogen signatures clustering around the poles. That was a signal. Hydrogen plus the right conditions equals water ice. And if water ice existed on the moon in meaningful quantities, then everything about the cost calculation of returning changed overnight. Water is heavy. Launching it from Earth into space costs an enormous amount of money per pound. Every drop of water consumed by astronauts on the International Space Station had to be lifted from Earth's surface at tremendous expense. If the moon already had water, frozen and waiting in permanently shadowed craters, then the moon stopped being a destination and became a supply depot. That realization is what quietly relaunched the entire conversation about going back. And when the NASA Lunar Reconnaissance Orbiter confirmed ice deposits at the South Pole in 2018, the conversation became a race. The Artemis program was announced with a language of exploration and national pride. The first woman on the moon, the next giant leap, a return to greatness. All of that is real. None of it is the whole story. Underneath the press releases, something harder and more urgent was driving the timeline. Other countries had read the same orbital data. Other governments had done the same math, and they were already moving. The next chapter reveals exactly what is frozen inside those craters, and why the nation that reaches it first holds something that rewrites the economics of space travel entirely. The south pole of the moon looks like the edge of the world. Craters stack on top of craters. Ridges cast shadows so long they never end. From orbit, parts of the South Pole look like they have been dipped in permanent black ink. And that darkness, that absolute billion-year-old darkness, is the most valuable thing in the inner solar system. Temperatures inside those shadowed craters drop to around minus 380 degrees Fahrenheit. That is colder than Pluto's surface, colder than almost anywhere else in the entire solar system that we have directly measured. These places are called permanently shadowed regions, and they have not seen a single photon of direct sunlight for potentially 2 billion years. Anything that falls into them stays. Over billions of years, comets, asteroids, and water-bearing meteorites have slammed into the moon. When water molecules from those impacts drifted toward the poles, they entered the shadow zones and simply froze. No atmosphere to move them, no geology to melt them, no sunlight to vaporize them. They stayed right where they landed and built up layer by layer, century by century. Scientists confirmed this water ice using multiple instruments across multiple missions. The L-Cross mission in 2009 deliberately crashed a rocket stage into the Cabeus crater near the South Pole, and then flew a spacecraft through the debris plume. The analysis came back positive. Water. Real water. Ice mixed into the regolith at a concentration that scientists described as similar to some of the driest deserts on Earth, but distributed across an enormous area. That might sound modest until you consider the scale. Scientists estimate the total deposits across the lunar poles could amount to billions of tons of water ice. Pause on that number. Billions of tons. Every astronaut stationed on a permanent lunar base would need around 1 ton of water per year to survive, drink, grow food, and recycle through life support systems. The South Pole deposits, if extractable, could sustain a human presence on the moon for an almost unimaginable stretch of time without a single resupply from Earth. But survival is only the beginning of why this matters. Water is 2 hydrogen atoms bonded to 1 oxygen atom. Split those bonds with electricity, and you get hydrogen gas and oxygen gas. Those 2 gases, combined in the right proportions and ignited, are among the most powerful rocket propellants ever used. The space shuttle's main engines burned liquid hydrogen and liquid oxygen. So do the engines on Artemis's Space Launch System rocket. If you can mine water on the moon, split it into propellant, and fill a rocket's tanks in lunar orbit, you have fundamentally changed the economics of going anywhere in the solar system. You no longer need to haul every drop of fuel up from Earth's deep gravity well at enormous cost. The moon becomes a fueling station sitting 250,000 miles from Earth, ready to launch missions toward Mars, the asteroid belt, or beyond. This is the real engine behind Artemis. Exploration with a commercial purpose, science with a strategic motive. And someone else already knows it. The next chapter explains who is moving fastest, what they have already accomplished, and why the timeline on NASA's schedule suddenly got a great deal more urgent. Nobody called it a race. But it is. In January of 2019, a Chinese lander touched down on the far side of the moon. For the first time in history, a spacecraft landed on the hemisphere that permanently faces away from Earth. The mission was called Chang'e 4, and it was a technical achievement that stunned engineers around the world. Communicating with a spacecraft on the far side requires a relay satellite positioned in a special orbit beyond the moon. China designed, launched, and operated that relay flawlessly. 2 years later, Chang'e 5 landed on the near side, collected about 4.5 pounds of lunar samples, and returned them to Earth. The first lunar samples retrieved by any nation since the Soviet lunar program ended in 1976. China had joined a club with a membership of 2, and they did it on the first attempt. Then they announced their next target, the South Pole. China's space agency published a roadmap calling for robotic landers at the lunar South Pole, followed by a crewed mission, followed by a permanent research station. Their stated goal is a functioning lunar base by 2040. Some analysts believe the internal schedule is faster. Here is why that timeline rattles people inside NASA. The South Pole has a finite number of genuinely good landing sites. The craters with the heaviest ice concentrations sit inside the permanent shadows, surrounded by terrain so rough and dark that landing there requires technology that does not fully exist yet. But right next to those craters sit the peaks of eternal light, ridges and crater rims that receive sunlight for up to 80 or 90% of the lunar year. Solar panels placed there generate power almost continuously. A base sited on those ridges with access to the shadowed craters below it would be in practical terms the best piece of real estate on the moon. There are only a handful of such locations. They are already mapped. Every agency knows exactly where they are. If China establishes infrastructure at one of those locations before Artemis lands, the physical and logistical reality on the ground shifts. You cannot simply ignore a base that another nation already built. The proximity of mining operations creates safety concerns. The radio frequency environment around a working base affects other missions trying to operate nearby. Nobody fires weapons. Nobody needs to. First presence creates facts on the ground that diplomacy has to work around. Russia, after decades of post-Soviet stagnation in lunar exploration, signed a cooperation agreement with China on joint lunar development. The European Space Agency has contributed hardware to Artemis, but maintains independent relationships with multiple partners. India landed near the South Pole in 2023, with Chandrayaan-3, the first spacecraft to successfully touch down in that region. Japan, South Korea, and the United Arab Emirates all have active lunar programs. The Moon has more visitors arriving every few years than it saw in the entire previous century. And in the middle of all this activity, the legal framework governing who can do what on the Moon was written in 1967, when only 2 countries had ever launched a satellite. What that framework allows, what it forbids, and how it is being quietly rewritten right now, is where the story gets truly unsettling. The answer is nobody, and that answer is becoming dangerously unstable. In 1967, the major spacefaring nations signed the Outer Space Treaty. The core principle was elegant and idealistic. Space belongs to all of humanity. No government can claim sovereignty over the Moon, Mars, or any celestial body. You can explore, you can operate, you cannot own. For 40 years, that framework held, mainly because almost nobody was actually going anywhere. Treaties are easy to honor when the resource being protected has no practical value yet. Then the ice was confirmed. Then fusion research started taking helium-3 seriously. Then the economics of cislunar space, the zone stretching from Earth to the Moon and back, started attracting investment from private companies worth hundreds of billions of dollars. Suddenly, the Outer Space Treaty looked like a lease agreement written for a neighborhood that had just discovered oil underneath it. The critical ambiguity in the treaty is the word sovereignty. The treaty bans national claims to territory. It says nothing clear about resources extracted from that territory. An analogy: international law says no country owns the high seas, but a fishing company can legally catch fish from the high seas and sell them. The fish, once caught, become property. The ocean itself remains common. Does the same logic apply to lunar ice? To helium-3 scooped from regolith? In 2015, the United States passed the Commercial Space Launch Competitiveness Act. It said Americans have the right to own resources they extract from space. Luxembourg passed similar legislation 2 years later. Other countries followed. None of these laws claim territory. All of them claim the product of labor performed on that territory. China and Russia rejected this interpretation. They argued that unilateral national laws carving up resource rights contradicted the spirit of the Outer Space Treaty and demanded a new international framework negotiated through the United Nations. Into this dispute stepped the Artemis Accords. NASA introduced the Artemis Accords in 2020 as a set of bilateral agreements between the United States and partner nations joining the Artemis program. They cover transparency, interoperability, the release of scientific data, and, critically, safety zones around active operations. Safety zones say that any Artemis partner operating on the Moon can establish a buffer area around their equipment and operations. Other actors are expected to avoid that zone to prevent harmful interference. The zones are temporary and tied to active operations. They are also potentially large, covering territory around landing sites, mining operations, and base infrastructure. China immediately pointed out that this framework, established outside the United Nations, was essentially the United States writing its own rules and inviting allies to sign on. Over 40 countries have now signed the Artemis Accords. China and Russia have signed neither. 2 parallel systems of lunar governance are forming in real time, one centered on Washington, one centered on Beijing, and the Moon with its finite number of prime locations and its frozen billions of tons of water, sits in the middle. The next chapter reveals a resource even more controversial than water, one that could power cities on Earth, and that the moon has been quietly collecting for 4 billion years. The solar wind never stops. Every second, the star at the center of our solar system blasts a stream of charged particles outward in every direction. Earth's magnetic field deflects most of it. The moon has no such shield. For 4.5 billion years, the lunar surface has sat fully exposed to that constant bombardment, absorbing whatever the solar wind carried. One of the things it carried is helium-3. Helium-3 is an isotope of helium with one fewer neutron than the common version. On Earth, it is extraordinarily rare. The entire annual global supply that we can produce or extract adds up to only a few pounds. Scientists use it in specialized medical scanners, ultra-cold physics experiments, and certain radiation detectors. The demand already outpaces supply. Governments treat it as a strategic resource and quietly stockpile it. On the moon, it is everywhere. Billions of years of solar wind exposure have embedded helium-3 across the top few yards of lunar regolith at concentrations that would seem absurd if the geology were not so well understood. Scientists estimate the moon holds somewhere around 1 million tons of it, though that figure carries real uncertainty and ongoing debate about how deep the deposits extend and how evenly they are distributed. The reason this matters comes down to one word: fusion. Nuclear fusion is the process that powers stars. Fuse hydrogen atoms together, and you release energy. Every major fusion experiment on Earth today uses a version of this process. The challenge is that standard fusion reactions produce fast neutrons, which damage reactor walls over time and make surrounding materials radioactive. Helium-3 fusion works differently. When you fuse helium-3 with another isotope called deuterium, the primary output is a proton, which carries an electrical charge and can be captured directly as usable electricity, with far fewer damaging neutrons produced. A helium-3 fusion reactor, in theory, would be cleaner, more efficient, and longer lasting than anything we currently operate on Earth. 100 pounds of helium-3, fused efficiently, could power a city the size of Dallas for a year. The moon holds 1 million tons of it. The catch is significant. Humanity has not yet built a working fusion reactor of any kind that produces more energy than it consumes. Helium-3 fusion adds another layer of technical challenge on top of that unsolved problem. Scientists at research institutions around the world are making genuine progress, but a working commercial helium-3 reactor could still be decades away. So why does this matter now? Because the mining infrastructure, the legal frameworks, the base locations and the logistics of extracting anything from the moon take decades to build. If fusion solves itself in 30 years, and nobody has yet secured access to helium-3 deposits, the scramble that follows would make the current lunar race look polite. Every country and company paying attention is making decisions today for a resource they cannot yet fully use. They are planting flags on a fuel depot that has not opened yet, and the moon has been patiently waiting, soaking up the solar wind, building up its inventory for 4 billion years. Something stranger than helium-3 may also be sitting in those same deposits. The next chapter explains what the South Pole's geography actually looks like, and why NASA engineers called the terrain there one of the most extreme environments ever targeted for a human landing. Stand at the lunar South Pole and look around. The horizon is only about 1.5 miles away, because the moon is smaller than Earth and its surface curves faster. The sky is always black, even when the ground is lit. Shadows stretch for miles and never shorten, because the angle of sunlight never climbs high enough to push them back. In one direction, a crater wall drops away into darkness so complete that your eyes find nothing to focus on. In the other direction, a ridgeline catches sunlight at a shallow angle, glowing gold in permanent slow-motion sunrise. This is the terrain that Artemis astronauts will actually step into. The lunar South Pole sits inside one of the oldest and largest impact structures in the entire solar system. The South Pole Aitken Basin is roughly 1,600 miles wide and about 5 miles deep. An asteroid hit the early moon with enough force to excavate a hole larger than the continental United States. and the scar never healed. The South Pole sits on the inner rim of this ancient wound, and the terrain bears the record of every subsequent impact layered on top of it. The craters here are dense, overlapping, and rough at every scale. What looks like a smooth plane from orbit is on the ground a field of boulders, sharp-edged rocks, and loose regolith resting at steep angles. The surface material at the South Pole has been gardened by billions of years of micrometeorite impacts until the top layer is a powdery, fine-grained nightmare for wheels, drills, and boots alike. Now add the temperature extremes. Sunlit surfaces near the poles can reach around 250 degrees Fahrenheit in direct light. Step 10 feet into shadow, and the temperature drops by hundreds of degrees within yards. Equipment designed to work in one thermal zone can fail catastrophically when it crosses into the other. Seals crack, lubricants freeze or boil depending on where they are sitting. Engineers call this the Terminator Zone problem, and solving it requires materials that simply did not exist when the Apollo suits were built. The permanently shadowed crater interiors add another layer of difficulty. To mine ice from those craters, robotic equipment must operate in near absolute darkness, at temperatures colder than any place on Earth, without direct communication with Earth, because the crater walls block line-of-sight signals. That equipment must carry its own power, its own navigation, and its own fault tolerance. Every breakdown is permanent, unless another robot is sent to repair it. And yet the science community is united in saying the South Pole is worth every bit of this difficulty. Because sitting right beside those frozen craters, on the ridges above them, are the peaks of eternal light. These high points receive sunlight for the vast majority of the lunar year. Mount a solar panel there, and you have a nearly continuous power supply. Run a cable down into the crater below, and you can power mining robots in permanent darkness. The geometry of the South Pole is one of the most remarkable coincidences in planetary science. Maximum resource concentration, sitting directly beneath maximum solar power availability. The challenge and the solution are stacked on top of each other, within a few miles of the same spot. The Artemis planners know exactly which ridges they want. They know which craters hold the densest ice deposits. They have a map. What they are building now, in orbit and on the drawing boards of aerospace companies, is everything else. What they are building in orbit deserves its own story entirely. Most people know about the International Space Station. Fewer people know that a second one is being assembled right now, in a completely different orbit, for a completely different mission. The Lunar Gateway is a small modular space station, being built in an orbit that swings between roughly 3,000 miles and 46,000 miles from the lunar surface. That unusual elongated path, called a near-rectilinear halo orbit, keeps the Gateway in continuous communication with Earth, while passing close to the Moon for several days during each orbit. It is not a destination by itself. It is a waypoint, a transfer hub, and a permanent outpost all at once. The first two modules launched separately, with the first expected to arrive in lunar orbit in the mid-2020s. Partner nations, including Canada, Europe, Japan, and the United Arab Emirates, are contributing hardware. Canada is providing the robotic arm. Europe is contributing a communications and refueling module. Japan is building the habitation and logistics module. The Gateway is the most international construction project in space since the original station in low Earth orbit. Why build it there instead of in low lunar orbit? The answer is fuel efficiency and access. The halo orbit requires very little propellant to maintain. Spacecraft arriving from Earth can dock at the Gateway with less fuel than landing directly on the Moon. Crew and cargo can be staged there, assembled, checked, and then descended to the surface in a dedicated lander. The Gateway acts like a base camp at high altitude on a mountain climb. The real summit push starts from there. The strategic purpose runs deeper than the engineering. A permanent human-tended facility in lunar orbit creates a continuous legal and operational presence in cislunar space. Any future mission from any country or company planning to operate around or on the Moon has to navigate around an infrastructure that is already there. The Gateway establishes facts in space the same way a remote research station establishes facts in Antarctica. China recognized this logic and announced plans for their own lunar orbit station. in a parallel program called the International Lunar Research Station, developed with Russia and open to other national partners. Their proposed orbit is different from Gateway's. Their architecture is designed around their own rockets and their own landers. Two separate lunar orbit infrastructures, two separate surface access systems, two separate frameworks for who owns what. In a more optimistic timeline, Gateway and the Chinese station eventually cooperate the way the early American and Soviet space programs eventually did, cautiously, slowly, but usefully. In a less optimistic timeline, two incompatible systems orbiting the same moon create operational conflicts with no clear authority to resolve them. The Gateway carries another purpose that almost never appears in press releases. It serves as the staging point for something beyond the moon entirely. The orbit it uses can, with the right propulsion, extend outward towards deep space destinations. Its life support and habitation systems are designed with longer missions in mind. Every technology validated on the Gateway, every medical protocol, every recycling system, every power management solution feeds directly into the mission that Artemis is ultimately rehearsing for. That mission is 8 months each way, with no resupply possible, and a destination where the gravity is nearly 2.5 times stronger than the moon's. The next chapter explains exactly how the moon prepares us for Mars, and why skipping the moon and going directly would likely be a fatal mistake. Going to Mars without first going to the moon would be like crossing the Atlantic for the first time in a submarine you had never tested in a harbor. The distances involved in a Mars mission are nearly incomprehensible in human terms. The moon sits about 240,000 miles away. Mars, at its closest approach, is roughly 100 times farther. A one-way trip takes around 7 months. Once a crew departs, there is no abort option. If a system fails halfway to Mars, no rescue is possible. If a crew member gets seriously ill after entering the Martian gravity well, no evacuation flight can reach them for years. Every piece of hardware, every medical protocol, every life support system must work the first time, and every time for the entire duration of the mission. The moon gives us a place to find out what does not work before those failures become irreversible. Consider the life support problem. The International Space Station uses a sophisticated system that recycles water from urine, condensed breath, and equipment cooling loops. It currently recovers around 90% of the water aboard. For a Mars mission, 90% is a slow death. Engineers calculated that a Mars-bound crew needs water recovery rates above 98%. That gap, from 90 to 98, has taken decades of engineering to close, and the final testing ground for those systems is the lunar surface. Astronauts living on the moon for 30, 60, or 90 days will stress test next-generation life support in conditions that the International Space Station cannot replicate. Low gravity, regolith dust contamination, temperature swings, and the psychological weight of genuine isolation all interact with hardware in ways that laboratory testing misses. The radiation problem is even more pressing. Inside Earth's magnetic field, astronauts on the International Space Station receive roughly 10 times the radiation dose of someone on the ground. Beyond that magnetic field, the dose increases sharply. Solar particle events, sudden bursts of charged particles from the star at our system center, can deliver a dangerous dose in hours. Galactic cosmic rays, high-energy particles from outside our solar system, penetrate almost any reasonable thickness of metal shielding and deposit their energy deep in tissue and bone. A lunar mission of 30 days delivers a radiation dose that scientists consider acceptable within career limits. A 7-month Mars transit, followed by a surface stay and a 7-month return, accumulates a dose that currently exceeds the lifetime limits set for astronauts by all major space agencies. Either those limits must be revised with new medical evidence, or new shielding technologies must be developed and tested. The moon is the only off-Earth location we can reach quickly enough to test those shielding solutions, measure their performance in real deep space radiation conditions, and bring crews home if the results are alarming. Food production compounds the challenge. Every calorie eaten on a Mars mission must either launch from Earth or grow on board. A 2-year round trip for a crew of 4 requires thousands of pounds of food unless a significant fraction of it can be grown in transit and on the surface. Growing food in reduced gravity, under artificial light, in a closed-loop system, while managing carbon dioxide and bacterial contamination has never been done beyond low Earth orbit. The Moon is where we practice. Everything learned there feeds into the Mars mission architecture. Every failure on the Moon is a survivable data point. Every failure on Mars is a tragedy with no witness. And before any of that can happen, one physical obstacle standing between humans and every deep space destination must be directly confronted. You cannot see it, you cannot feel it, and by the time it starts killing you, the damage is already done. Radiation beyond Earth's magnetic field is the single most dangerous physical obstacle between humanity and long-duration spaceflight. Engineers can design rockets that do not explode. They can build life support systems that do not fail. They can solve every mechanical problem given enough time and money. Radiation does not respond to engineering in the same way, because it is not a malfunction, it is the environment itself. Here is how it works at the scale of a human cell. Cosmic rays and energetic solar particles slam into the atoms inside your body. When a high-energy particle passes through a strand of DNA, it can snap the strand or alter the sequence of chemical information encoded in it. Your cells repair most of this damage. They have been doing it since life began. The problem in deep space is the rate. The dose arriving beyond Earth's magnetic field is high enough that repair systems fall behind. Long-term effects include elevated cancer risk, cataracts, cardiovascular damage, and, particularly relevant to Mars mission planning, neurological changes. Studies of rodents exposed to simulated cosmic ray environments showed measurable changes in brain function, including impaired memory and increased anxiety-like behavior after extended exposure. Similar research using data from astronauts who flew long missions suggests that white matter in the brain shows changes consistent with accelerated aging. NASA calculated that a Mars astronaut following a nominal mission profile would absorb a career radiation dose that exceeds current safety limits before they ever set foot on the Martian surface. 3 solutions are being pursued simultaneously. The first is better shielding. The problem with traditional metal shielding is that high-energy cosmic rays interact with it and produce secondary radiation particles, sometimes making the dose behind the shield worse than in front of it. Hydrogen-rich materials, including water, polyethylene foam, and certain plastics, absorb cosmic rays with far less secondary scatter. Designs being tested now use water walls around sleeping quarters, the logic being that the crew spends roughly a third of their lives in those areas, and maximizing shielding there significantly reduces total exposure. The second solution is biological. Research teams are studying whether certain drugs, some already in clinical trials for cancer patients, can prime DNA repair mechanisms before and during radiation exposure to reduce the rate of damage accumulation. A daily pill that halves radiation damage would change the mission mathematics entirely. The third solution is speed. The faster the transit to Mars, the less total dose accumulated. Nuclear thermal propulsion, a technology tested briefly in the 1960s and now being revived in classified and unclassified programs, could potentially cut Mars transit time from 7 months to around 4 months. Less time in deep space means less radiation absorbed. All 3 solutions are in active development. None is fully proven. And all of them will see their first real-world test on the Moon, the only place humans can go beyond Earth's magnetic protection, and come home inside a reasonable time frame if something goes wrong. The astronauts selected for Artemis lunar surface missions understand they are the test subjects for the Deep Space Radiation Research Program. They signed up for it anyway. But radiation is only one of the hazards waiting on the lunar surface. The other one coats every surface, clogs every filter, and may prove more persistent than the radiation itself. It gets into everything. The Apollo astronauts noticed it within hours of their first moonwalks. Lunar dust coated their suits from boot to helmet. It worked into the joints of their gloves and the seals around their visors. It scratched the optical surfaces of cameras. It abraded the outer layers of their suits faster than engineers had predicted. By the time they climbed back into the lunar module, the habitat smelled like gunpowder, which is how astronaut Harrison Schmitt described it. And the dust was inside the cabin, floating in the air and settling on every surface. Lunar regolith is unlike any dust on Earth. On our planet, Wind and water smooth particles over millions of years into rounded grains. The Moon has neither. Its surface has been pulverized for 4.5 billion years by micrometeorites hitting at high speed, and the resulting particles are jagged, sharp-edged and fractured at microscopic scales. Under a scanning electron microscope, a grain of lunar dust looks like broken glass. The particles are also electrostatically charged. The day side of the Moon receives ultraviolet radiation from the star at our system's center, which strips electrons from surface particles and leaves them positively charged. The night side accumulates electrons from the solar wind and charges negatively. At the terminator, the moving boundary between light and dark, particles levitate off the surface and move in streams driven by electrostatic forces. Spacecraft instruments have detected a faint haze of dust extending miles above the lunar surface. This creates a contamination problem with no easy solution. Every time an astronaut comes in from a moonwalk, they bring dust into the habitat. The particles are too small for most filters to catch efficiently. Breathing them may cause effects similar to silicosis, the lung disease that affects miners and quarry workers exposed to fine silica dust on Earth. Long-duration lunar residents breathing even trace amounts of suspended regolith face a cumulative health risk that the Apollo missions, which lasted only a few days on the surface, never had to fully confront. The dust also destroys equipment. It coats solar panels and reduces their efficiency by absorbing and scattering light. It jams mechanical joints by working into bearing surfaces. It degrades thermal coatings by changing the reflective properties of surfaces that need to reject heat precisely. An experiment left on the lunar surface by Apollo astronauts included a mirror array used to measure the Moon's distance from Earth by bouncing laser pulses off it. Decades later, that mirror array is significantly less reflective than when it was placed. Dust accumulation is the suspected cause. NASA and private companies developing lunar hardware are treating the dust problem as one of the top 3 engineering challenges on the entire Artemis manifest, alongside radiation and life support. Proposed solutions include electrostatic dust shields that use vibrating electric fields to repel particles from surfaces, self-cleaning coatings that shed particles when exposed to ultraviolet light, and airlock designs that use powerful compressed gas or mechanical brushing to clean suits before they enter the habitat. Solving the dust problem on the Moon means solving it permanently for every planetary surface humans ever visit. Mars has dust of its own, though Martian dust is chemically different and electrostatically less aggressive. The solutions developed for the Moon will carry forward. But underneath the dust, there is something that almost nobody in the public conversation about lunar exploration talks about. An ancient structure hiding just below the surface that could change where humans actually live on the Moon. The Moon built its own shelter billions of years ago and then forgot about it. When the Moon was young, it was volcanically active. Vast floods of molten rock poured across the surface and carved the broad, dark plains we can see from Earth with the naked eye, the features people call the man in the Moon. As that lava flowed, the outer surface of the flow cooled and hardened, while molten rock continued to move beneath it, like water flowing under ice. When the eruption stopped and the remaining lava drained away, it left behind long, hollow tunnels running just below the surface. These are called lava tubes, and we have them on Earth. The largest ones here are impressive. Some in Hawaii run for miles and stand 30 or 40 feet tall inside. But the Moon's lower gravity, roughly 1/6 of Earth's, allowed lava to move faster and in much greater volume. Lunar lava tubes are, by analysis of orbital radar data and surface pits where the ceilings have partially collapsed, orders of magnitude larger than anything on Earth. Scientists studying a pit near the Mare Tranquillitatis region, visible from orbit as a clean vertical hole dropping into darkness, calculated that the cavern beneath it could be several hundred feet wide and extend for potentially miles. Radar measurements from Japan's Kaguya orbiter detected what appeared to be an intact lava tube stretching for more than 30 miles and possibly more than 1/3 of a mile wide. To put that in perspective, a tunnel 1/3 of a mile wide is wide enough to fit a large sports stadium inside it and still have room for roads on either side. These structures already solve 2 of the biggest problems facing a permanent lunar base. First, radiation. The rock ceiling above a lava tube Even just 30 feet of it provides shielding equivalent to years of surface exposure reduced to a manageable dose. The billions of tons of regolith overhead act as natural radiation armor that no spacecraft wall, however cleverly engineered, can match by weight. Second, temperature. The lunar surface swings between extremes of 250 degrees Fahrenheit in daylight and nearly 200 degrees below zero at night. A lava tube, insulated by the rock around it, maintains a stable temperature of around -4 degrees Fahrenheit year-round. That is cold, but it is manageable and constant. Constant is valuable when building life support systems. A habitat inside a lava tube would need a fraction of the thermal insulation and radiation shielding of a surface structure. Power budgets shrink. Engineering margins grow. The structure itself may require pressurization and heating, but the massive rock above it solves the two hardest problems for free. The challenge is access and verification. We can see the pit entrances from orbit. We do not yet have a robot that has descended into one and confirmed what is inside. The ceiling could be stable or fractured. The floor could be smooth or covered in collapsed rock. Every assumption about the interior rests on indirect data. Artemis planning documents acknowledge lava tubes as candidate long-term habitation sites, but do not include them in the near-term mission architecture. The first bases will be on the surface, near the poles, near the ice. The lava tubes wait further inland, in the equatorial regions where the Apollo missions landed. Sending a robot into one of those pits is on several mission wish lists. The first team to go inside and confirm a habitable tube will have found something worth more than any crater full of ice. But before any permanent base gets built anywhere on the moon, whether on the surface or underground, one obstacle threatens to complicate everything. The moon's geological behavior, active, unpredictable, and strong enough to shake buildings to pieces. Most people assume the moon is geologically dead. It formed 4.5 billion years ago. Its volcanoes went quiet over 1 billion years ago. Its interior cooled and solidified. The story of lunar geology seems to be a story of deep time and slow stillness. That assumption is wrong. In the 1960s and 70s, Apollo missions placed seismometers on the lunar surface. Those instruments ran for years and sent back data that confused scientists for decades. The moon shakes regularly. Some tremors come from meteorite impacts, but thousands of the recorded events were genuine moonquakes, originating inside the moon itself, and their behavior was unlike anything measured on Earth. The strangest feature of moonquakes is how long they last. On Earth, an earthquake releases its energy and fades within a minute or two. Rock on Earth contains water in its crystal structure, and that water absorbs seismic energy efficiently, damping the vibrations quickly. The moon's interior is dry, completely dry. Seismic waves bounce back and forth inside the moon the way sound rings inside an empty metal tank, with almost nothing to absorb them. A moderate moonquake can shake the ground for 10 minutes or more. Some recorded moonquakes reached a magnitude of 5 on the Richter scale, strong enough to topple unsecured structures, damage pipelines, and fracture seals in pressurized habitats. A team of scientists re-examined the Apollo seismic data in recent years and found something that raised serious concern. They identified a band of shallow moonquakes concentrated near the South Pole. These quakes occur at depths shallow enough to affect the surface directly. One analysis concluded that ongoing thermal contraction of the moon, as its interior slowly continues to cool and shrink, is creating thrust faults near the South Pole, places where sections of crust push against each other and periodically slip. One of those thrust faults was identified within 18 miles of a prime candidate landing site for Artemis. 18 miles is close enough that infrastructure connecting a landing zone to a mining operation, the roads, cables, and pressurized tunnels that any serious base would require, could pass through or near seismically active terrain. Building on the moon requires the same seismic engineering discipline used in earthquake-prone cities on Earth. Reinforced foundations, flexible connections between pressurized modules, automatic shutoffs on fluid and gas systems, and structural designs that absorb shaking without failing catastrophically. None of this is impossible. Japanese engineers have been building earthquake-resistant structures for over a century in one of the most seismically active countries on Earth. The same principles apply on the Moon, but the engineering costs time, money, and mass, all of which are scarce on a lunar mission. The deeper implication of lunar seismicity is what it says about the interior. A moon that is still contracting thermally, still generating thrust faults, and still producing magnitude 5 quakes, is a moon that retains more internal energy than models predicted. That internal energy may play a role in the magnetic anomalies mapped across the lunar surface, scattered patches of magnetism with no obvious geological explanation, each one potentially the remnant of a catastrophic event billions of years ago. That event, and what it tells us about the early history of both the Moon and the Earth, is a story that rewrites what we thought we understood about where we came from. The Moon did not form quietly. The dominant scientific model, supported by chemistry, physics, and the isotopic signatures of returned lunar samples, says the Moon was born from a catastrophe. Around 4.5 billion years ago, an object roughly the size of Mars slammed into the early Earth at an oblique angle. The impactor, which scientists call Theia, was not a rogue asteroid. It was a protoplanet, a body that had formed in the same region of the solar system as Earth, and gradually drifted into a collision course. The impact vaporized a significant fraction of both bodies. A cloud of superheated rock vapor surrounded the young Earth. Over thousands of years, that cloud cooled. The particles clumped together under gravity, and the Moon assembled itself from the debris of two worlds merging. This is confirmed by the isotopic composition of lunar samples. The ratio of oxygen isotopes in moon rocks matches Earth's mantle with extraordinary precision, far beyond what random capture of an outside body would produce. The Moon and Earth are, at the elemental level, siblings made from the same material. The Apollo samples proved this. Every subsequent analysis reinforced it. Now, the scattered magnetic anomalies mapped across the lunar surface are pointing toward a refinement of that story. These anomalies appear as patches of magnetism embedded in the crust, some hundreds of miles wide, and many of them cluster on the side of the Moon directly opposite large impact basins. The pattern suggests that massive impacts on one side of the Moon sent shockwaves through the interior and focused them on the opposite side, scrambling the crust and potentially remagnetizing it when remnant magnetism from the early lunar core was still active. If that model is correct, it means the Moon's interior was still generating a magnetic field for hundreds of millions of years after its formation, far longer than most models suggested. It also means the South Pole Aitken Basin, the enormous ancient impact scar where Artemis plans to operate, generated shockwaves that left their signature on the entire Moon. The early solar system was extraordinarily violent. The Earth absorbed dozens of large impactors in its first billion years. Most of them vaporized into the planet's interior. The one that made the Moon did something different. It struck at the right angle, at the right speed, and with the right mass to throw material into orbit, rather than simply adding to Earth's bulk. That geometrical coincidence produced a Moon of almost exactly the right size to stabilize Earth's axial tilt. Without the Moon's gravitational influence, Earth's tilt would wobble chaotically over millions of years, driving climate swings severe enough to sterilize the surface. The presence of the Moon holds that tilt steady within a narrow range that allows the relatively stable seasons and climate zones that life on Earth depends on. The catastrophe that made the Moon was also, indirectly, a precondition for complex life on Earth. Artemis astronauts collecting samples from the South Pole Aitken Basin will be picking up pieces of the Moon's most ancient crust, material that predates even the giant impact that formed the basin itself, rocks from the first few 100 million years of solar system history. No sample from this region has ever been returned to Earth. Scientists expect those samples to rewrite the timeline of how rocky planets form. And inside those ancient rocks, frozen at the bottom of craters, mixed into the ice that Artemis ultimately came to find, there may be something else entirely. Water was the headline. Water is not the only thing down there. When the L-Cross spacecraft flew through the debris plume of a deliberately crashed rocket stage at the lunar South Pole, its instruments detected more than ice. The analysis that followed took years to fully process and publish, and the results were quiet enough that they barely registered in mainstream coverage. The permanently shadowed craters at the South Pole contain a mixture of frozen compounds that scientists describe as resembling the composition of a comet nucleus. Along with water ice, instruments detected carbon dioxide, carbon monoxide, ammonia, hydrogen sulfide, methanol, ethanol, and traces of compounds that fall under the broad category of organic chemistry, molecules containing carbon chains that, on Earth, are the building blocks of biology. None of this proves life. To be precise, the detection of organic compounds on the Moon does not suggest biology. The Moon has no biosphere, no liquid water, and has been geologically inactive for over 1 billion years. The organic molecules almost certainly arrived via cometary impacts, the same comets that seeded early Earth with carbon compounds and then froze in place inside the cold traps. But the presence of that chemical inventory raises a scientific question with significant implications. If the Moon has been collecting and preserving cometary material in its cold traps for billions of years, and if we retrieve and analyze that material, we may be reading a frozen chemical record of what the early solar system was delivering to Earth during the period when life first appeared. The Moon's South Pole craters are, in this sense, a time capsule. The oldest ice layers at the bottom of those craters may preserve chemical signatures from 4 billion years ago. Earth's geological activity, plate tectonics, volcanic resurfacing, erosion, and biological activity has erased almost every record of that period from our own planet. The Moon preserved it in ice. Astrobiologists have pushed to include sample return from permanently shadowed regions as a priority in Artemis mission science objectives. The technical challenge is significant. Collecting samples from the interior of those craters requires robotic systems that operate in total darkness at temperatures close to absolute zero. And the samples must be kept cold during the return journey to Earth, or the volatile compounds evaporate. A warm sample is a destroyed sample. Cold sample return technology is currently under development. Missions to comets and asteroids have demonstrated some of the required techniques. But bringing back a frozen, uncontaminated sample from a permanently shadowed crater is an engineering challenge that has not been fully solved. If those samples are ever returned and analyzed, scientists expect the data to constrain the timeline and chemistry of the late heavy bombardment, the period roughly 3.5 to 4 billion years ago, when the inner solar system was pelted with impactors at a dramatically elevated rate. Understanding that bombardment helps explain why life appeared on Earth when it did, and whether the same delivery of chemical ingredients reached Mars. Somewhere inside those frozen layers may be the chemical moment before life on Earth began. The Moon held onto it, while Earth erased the evidence. And while scientists build the cold sample return systems needed to read that record, the political and legal frameworks governing what can be done with lunar resources are being written right now by people and institutions whose decisions will define who benefits from everything the Moon contains. Space law is being rewritten in real time, and most people have no idea it is happening. The Outer Space Treaty of 1967 was a document of its moment. Two superpowers were racing to demonstrate technological dominance. Both wanted rules that prevented the other from claiming the Moon as sovereign territory. The treaty solved that problem elegantly. No nation can claim any celestial body as its own. Space belongs to all humanity. That principle remains intact. What is collapsing is the consensus around everything else. The Artemis Accords, signed by over 40 nations as of early 2205, establish a set of behavioral norms for cislunar operations. They require transparency in activities, open sharing of scientific data, deconfliction of operations through notification, and interoperability of rescue and emergency systems. These are reasonable, largely uncontroversial provisions. The provision drawing the most scrutiny is the safety zone clause. An Artemis signatory operating on the Moon can designate an exclusion buffer around its activities to prevent harmful interference. The zone is defined as temporary and operational, tied to specific ongoing activities rather than permanent territorial claims. The practical effect, however, is that a company or agency operating a mining installation on the lunar South Pole can legally request that all other operators stay clear of a surrounding area. How large is that area? The Accords do not specify precise dimensions. That ambiguity is intentional and troubling in equal measure. depending on who you ask. Proponents argue that safety zones are functionally similar to maritime zones around working vessels, a practical operational necessity, not a sovereignty claim. Critics argue that on a body with a limited number of viable resource extraction sites, large safety zones around the best locations effectively monopolize them without formally claiming territory, a distinction without a meaningful difference. China's position is that the Artemis Accords represent a framework written by one nation, endorsed by its allies, and designed to formalize American and partner nation commercial interests in space, under the language of international norms. They advocate for negotiating any new space resource framework through the Committee on the Peaceful Uses of Outer Space at the United Nations, where all nations have a voice. That process would take decades. By the time a UN-negotiated treaty on lunar resource rights reached ratification, multiple nations and companies would already be operating extraction systems at the South Pole under frameworks they had established unilaterally. The legal vacuum is filling itself, one agreement and one landed mission at a time. An unresolved question hangs over all of it. What happens when two operators claim overlapping safety zones at the same prime location? The Accords call for coordination and communication. They provide no enforcement mechanism. There is no lunar court. There is no peacekeeping force. The only tools available are diplomacy, and beneath that, the threat of geopolitical consequences back on Earth. The Moon, it turns out, is governed by the same mechanisms that govern international disputes on Earth: leverage, precedent, and the patience of whoever holds the better position. The next chapter reveals who is building the hardware that will actually land there first, and why the selection of that hardware changed the shape of the entire mission in ways the original planners never anticipated. When NASA announced that SpaceX had won the contract to build the human landing system for Artemis, the aerospace world went quiet for a moment. The vehicle selected was Starship. At the time of the award, Starship had never reached orbit. Its development program had destroyed multiple prototypes in dramatic fashion, the kind of footage that fills highlight reels and worries program managers in equal measure. And yet NASA chose it over more conventional competitors, including a proposal from a team led by Blue Origin, Jeff Bezos' space company, and Dynetics. The reason was money and capability combined. Starship was the only proposal that could land the required mass on the lunar surface within budget constraints, while also offering a credible path to reusability. The other proposals were larger, more expensive, and would require more launches to accomplish the same mission. Starship's sheer size, the largest rocket ever flown by a significant margin, meant it could carry more crew, more equipment, and more supplies in a single trip. The vehicle stands roughly 390 feet tall when assembled with its super heavy booster, taller than the Statue of Liberty by a wide margin. Its engines, burning liquid methane and liquid oxygen, produce a combined thrust that exceeds every rocket ever built. The first fully integrated orbital test flights in 2024 ended in explosions, but each failure generated data that drove engineering changes. By late 2004, Starship completed its first successful orbital flight, with the booster returning to the launch stand and being caught by the launch tower's mechanical arms. The dependence on Starship creates a single-point risk in the Artemis architecture. The program's ability to land humans on the Moon is now coupled to the development timeline of a vehicle built by a private company, subject to regulatory approvals, technical setbacks, and the priorities of a chief executive, Elon Musk, whose public statements about timelines have historically run ahead of schedule. NASA's own human landing system has no backup at the current mission architecture level. Blue Origin is developing a separate lunar lander called Blue Moon, under a different NASA contract, which could eventually provide redundancy, but it will not be ready for the first crewed Artemis landing. The selection of Starship also introduced a fuel depot requirement into the mission plan. Starship uses so much propellant that a single Falcon 9 class rocket cannot launch enough fuel to fill it for a lunar mission. The mission plan requires multiple tanker flights to fuel Starship in Earth orbit before it departs for the Moon. Each of those tanker flights is an additional launch, an additional point of failure, and an additional schedule dependency. Engineers call this orbital propellant transfer, and it has never been done before at operational scale. Test demonstrations have been conducted. Full operational capability for a crewed lunar mission requires a degree of reliable precision in zero gravity that represents a genuine technical challenge. The astronauts assigned to the first Artemis landing are fully aware that they will board a vehicle with the most ambitious technical pedigree of any crewed spacecraft in history. Ambitious, as one veteran astronaut put it in an interview, in both directions. But the hardware is only part of the Artemis story. The people selected to fly it represent a deliberate choice about what image America wants to project to the watching world. And that choice reveals something important about what this mission is really competing for. The name was chosen deliberately. Apollo was the Greek god of the sun. Artemis was his twin sister, goddess of the moon. The naming of NASA's return mission was an announcement embedded in mythology. This time, a woman would walk on the moon. The Artemis Astronaut Corps is the most diverse group ever assigned to a lunar program. The 4-person crew of Artemis II, announced in April of 2003 for a crewed lunar flyby, included Reed Wiseman as commander, Victor Glover as pilot, the first black astronaut assigned to a deep space mission, Christina Koch as mission specialist, the first woman assigned to a lunar mission, and Canadian astronaut Jeremy Hansen, the first non-American assigned to any lunar crew in history. That selection was not accidental. Every element of it was calculated to send a message to a global audience watching which nation is leading humanity's return to the moon. Space exploration has always carried a public diplomacy dimension. The Apollo program was not purely science. It was a demonstration of American technological supremacy at the height of Cold War competition. The images of American astronauts on the lunar surface were broadcast to every nation on Earth, and the message was clear. This is what American engineering and American ambition can accomplish. Artemis is competing for the same global attention in a different era with different rivals. China's space program has worked methodically to project an image of competence, ambition, and national confidence. Every successful Chang'e landing, every sample return, every far-side achievement is broadcast with careful messaging about Chinese scientific capability and the country's place in the future of space exploration. Nations in Africa, Southeast Asia, and Latin America that are choosing technological partners for the coming decades are watching both programs and drawing conclusions. The inclusion of the first woman on a lunar surface mission matters to that competition in a concrete way. Billions of people who have never identified with the image of a white male astronaut planting a flag have the opportunity to see someone who looks more like them standing on another world. That is a soft power instrument of significant magnitude in the contest for global alignment in cislunar space governance. Victor Glover's assignment to Artemis II carries the same weight. The Apollo program unfolded during a civil rights movement that it largely ignored. The astronaut corps of that era was exclusively white and exclusively male by institutional design. Artemis corrects that record in a way that no press release could accomplish, by putting those astronauts on the mission itself. The Canadian inclusion was a diplomatic transaction with real value. Canada's contribution of the robotic arm to the Lunar Gateway secured a Canadian seat on a lunar flyby mission, binding a key ally to the Artemis architecture and demonstrating that the program delivers tangible benefits to partner nations. Critics observe that the diverse crew composition, however meaningful symbolically, does not resolve any of the harder questions about who benefits from lunar resources, how safety zones will be governed, or what legal framework protects smaller nations from being shut out of the moon's wealth. A diverse astronaut in a spacesuit does not automatically produce equitable space governance. Those critics are correct, and the harder questions are the ones that determine whether Artemis becomes the foundation of a sustainable human future in space, or the opening chapter of a conflict that plays out over the next century on a world 240,000 miles away. Everything the program has built, the gateway, the lander, the South Pole target, the Accords, the science, the crew, it all arrives at a moment in history that will look, in retrospect, like a hinge. What comes after the first landing is stranger, more consequential, and more uncertain than anything that came before it. Earth is a terrible archivist. Our planet is geologically violent. Tectonic plates grind together, fold mountains, and drag ancient crust down into the mantle, where it melts and resets. Erosion by wind and water grinds surface rock into sediment over millions of years. Volcanic eruptions bury and transform whatever came before. The oldest surface rocks on Earth are around 4 billion years old, and finding them requires traveling to specific remote shield regions in Canada, Australia, and Greenland. Rocks from the first 500 million years of Earth's existence are effectively gone. That missing chapter covers the period when life may have first appeared on our planet, the chemistry that allowed the first self-replicating molecules to form, the conditions of early oceans, the rate of asteroid impacts during the late heavy bombardment. All of it falls inside the time window that Earth's geology has erased. The Moon has not erased it. The Moon has no plate tectonics, no liquid water on the surface, no significant atmosphere. Erosion happens, but only by the slow grinding of micrometeorite impacts over billions of years, a process that scratches the surface without reshaping it fundamentally. Ancient terrain on the Moon stays ancient. Craters from 4 billion years ago are still sitting where they formed, slightly softened by time but structurally intact. The Apollo rock samples included specimens over 4 billion years old. Some exceeded 4.5 billion years, placing them among the oldest solid material ever directly handled by a human being. Studying these rocks tells geologists about conditions in the early solar system, the composition of the materials that built the Earth-Moon system, and the timing of major impact events. Future sample return missions targeting specific geologic units on the Moon could recover material from the precise era that Earth's geological record has lost. Scientists at the Lunar and Planetary Institute have identified regions on the Moon where ancient crustal material, called the lunar highlands, preserves a chemical and isotopic record dating back to within the first 100 million years of the solar system. Here is the scientific stakes. The origin of life on Earth is one of the deepest unsolved questions in biology and chemistry. Most origin of life hypotheses require liquid water, organic molecules, and a period of relative stability when complex chemistry could proceed without constant destruction by large impacts. If the Moon's impact record shows that the late heavy bombardment ended decisively before a certain date, that gives scientists a window during which early Earth could have supported stable chemistry. If the bombardment lasted longer or was more erratic, the timeline for life's origin shifts accordingly. The Moon is the calibration tool for Earth's early history. Nailing down the impact rate and timing with precision requires returning samples from specific, well-dated lunar units, a goal that Artemis science planning has explicitly included. One sample from the right location on the Moon could sharpen the timeline of Earth's history by hundreds of millions of years. What gets preserved in the rock record isn't the only scientific prize waiting on the Moon's surface. Beneath the regolith, distributed across the entire globe of the Moon, is a set of mineral deposits that have very direct relevance to technology being manufactured on Earth right now, today, in quantities that are already becoming critically short. Every lithium-ion battery in every electric vehicle contains cobalt. Every smartphone screen uses rare earth elements to produce accurate color. Every wind turbine generator uses powerful permanent magnets built from neodymium. Every electric motor in every modern appliance contains materials that require rare earth elements in their production. The global supply of these elements is finite, geographically concentrated, and under increasing pressure from the accelerating demand of green energy technology and consumer electronics. Roughly 85% of the world's rare earth processing currently runs through facilities in China, a concentration that creates supply chain vulnerabilities that governments in the United States, Europe, Japan, and elsewhere have identified as critical national security concerns. The Moon's surface contains these elements. Orbital spectroscopy missions have confirmed the presence of rare earth element signatures across multiple lunar regions. The South Pole Aitken Basin, the massive ancient impact crater on the far side, excavated material from deep within the lunar mantle during its formation. The exposed material includes minerals not commonly found on the surface, some of which contain rare earth elements in concentrations worth studying closely. Scientists analyzing the composition of the basin floor have found signatures consistent with minerals called pyroxenes and plagioclase that carry rare earth content. Beyond the basin, the lunar maria, the dark basaltic plains covering much of the near side, contain ilmenite, a mineral rich in titanium and iron. Titanium is lightweight, extremely strong, and corrosion-resistant. Its aerospace applications are extensive. Ilmenite also happens to be one of the primary targets for oxygen extraction using high-temperature processing, making it doubly valuable for a surface base. Uranium and thorium, both radioactive elements useful for nuclear power generation and scientific dating, are confirmed present in elevated concentrations in certain lunar regions. The Lunar Prospector mission measured thorium concentrations at the surface using gamma-ray spectroscopy, finding a significant hotspot on the near side associated with a volcanic region called the Procellarum KEREP. Terrain. KREP stands for potassium, rare earth elements, and phosphorus, a geochemical signature indicating ancient, mineral-rich volcanic activity. The confirmed science is the presence of these elements in the surface material. What is not yet confirmed is whether they exist in concentrations high enough to make extraction economically viable relative to Earth-based mining, once the cost of operating on the Moon is factored in. For the near term, lunar rare earth mining faces an economic barrier. Extracting minerals on the Moon and transporting them back to Earth costs far more than mining them on Earth, even from difficult or environmentally sensitive deposits. Analysts are clear that lunar mineral extraction for Earth's supply is a long-term proposition, measured in decades and dependent on the development of a mature cislunar infrastructure that dramatically reduces transport costs. For in-situ use, the calculation is different. Building structures, manufacturing components, and producing fuel on the Moon using local materials avoids the transport cost entirely. A titanium alloy produced from lunar ilmenite and used to build a lunar-based structure costs nothing to ship from Earth. The economic viability of lunar resource extraction shifts depending on whether the destination is Earth or the Moon itself. And as the base grows and the infrastructure matures, the list of materials that can be sourced locally grows with it. The Moon's resources, taken together, represent a supply chain node that could either ease Earth's material pressures in the long term or trigger an entirely new category of international competition. The outcome depends almost entirely on who gets there first and what legal framework governs what they do next. And that competition carries risks that go beyond economics. Imagine two mining operations established at the lunar South Pole, separated by a few miles. One is American-led, operating under the Artemis Accords, extracting water ice from a permanently shadowed crater to produce propellant. The other is Chinese-led, operating under a different legal interpretation, extracting ice from an adjacent crater for the same purpose. Both claim their operations are legal. Neither recognizes the other's legal framework as binding. The ice deposits are finite. The best extraction sites overlap in places. No treaty currently in force provides a mechanism to resolve that dispute. This is a scenario that space policy researchers at institutions including the Secure World Foundation and the Space Policy Institute at George Washington University have analyzed in published work. Their conclusion is consistent. The existing legal architecture for space, built around the Outer Space Treaty of 1967 and the never fully ratified Moon Agreement of 1984, was designed for exploration, not exploitation, and it contains significant gaps when applied to competing resource extraction operations. The Outer Space Treaty prohibits national appropriation of the Moon by claim of sovereignty, but it says nothing about whether a company, operating under a national license, can hold exclusive rights to the output of a specific extraction facility. The distinction between owning the Moon and owning the minerals you extract from it is legally ambiguous, and different nations are currently exploiting that ambiguity in opposite directions. The risk is a creeping form of de facto territorial control, achieved through infrastructure rather than formal claims. A nation that builds a base at the best South Pole location, establishes a fuel production facility, and maintains a permanent presence, is effectively controlling that location, regardless of what any treaty says about formal sovereignty. The Antarctic model, where territorial claims were frozen by international agreement, succeeded because no nation had yet invested significant permanent infrastructure in Antarctica when the treaty was negotiated. The Moon may not afford that luxury. By the time international negotiators could agree on a binding framework, the infrastructure competition may have already determined outcomes on the ground. The economic stakes amplify the pressure. A functioning lunar fuel depot, once operational, generates revenue and strategic leverage. A nation that controls the most efficient propellant source in cislunar space has commercial and strategic leverage over every other actor that depends on it for deep space missions. That leverage is worth protecting. History offers uncomfortable analogies. Competition over strategically valuable geographic features has produced conflict before on sea lanes in mountain passes, over river systems. The lunar South Pole's combination of water, ice, solar power, and gravitational advantage makes it the most strategically valuable geographic feature humanity has yet identified beyond Earth. Whether the competition over it resolves peacefully depends on decisions being made now, in policy offices and international forums, by people working against a timeline set not by diplomacy, but by rocket launch schedules. The resource race runs alongside a health risk that is less visible, but equally real. Living and working in the lunar environment will impose biological costs on every person who stays there, and current medicine does not have complete answers for all of them. 40 years of continuous human presence on the International Space Station has taught medicine an enormous amount about what happens to the human body in microgravity. Bone density decreases, muscle mass shrinks, fluid shifts toward the head, putting pressure on the optic nerve and causing vision changes that affect a significant percentage of long-duration astronauts. The immune system behaves differently. Cognitive function under sustained stress and isolation changes in measurable ways. The Moon adds new variables. Lunar gravity is roughly 1/6 of Earth's gravity. This means the human body is not in freefall, as on the space station, but it is also not bearing the full weight-bearing load it evolved for over millions of years of Earth life. The long-term physiological effects of 1/6 gravity on human health across periods of months or years have never been directly studied. There are no long-duration studies on partial gravity because no human has ever spent more than a few days on the Moon, and no rotating station that simulates partial gravity has ever been built. Bone and muscle loss models from the space station suggest that 1/6 gravity would cause some degradation, but possibly less than zero gravity. The precise rate and magnitude remain unknown, classified by researchers as a critical knowledge gap in lunar mission planning. Radiation, as discussed earlier, is a confirmed and severe concern. Added to the cosmic ray background is the psychological dimension of radiation exposure itself. Astronauts on the lunar surface would know their cumulative dose is rising daily. The psychological weight of knowing you are accumulating an increased lifetime cancer risk without being able to see or feel the damage has received limited formal study in the context of surface operations, but is recognized in space medicine as a meaningful stressor. Lunar dust is a separate and underappreciated problem. Apollo astronauts reported dust contamination as one of the most persistent practical challenges of surface operations. Lunar regolith particles are not rounded by water erosion, as most Earth dust is. They are jagged, abrasive, and electrostatically charged, clinging to suits, equipment, and surfaces with remarkable tenacity. Harrison Schmitt, the geologist astronaut who walked on the Moon during Apollo 17, developed symptoms resembling hay fever from dust that infiltrated the habitat module, despite precautions. In a long-duration habitat, where suits are donned and removed repeatedly over months or years, fine lunar dust particles could accumulate in the living environment. Inhaled particles of the size found in lunar regolith can reach deep into the lungs. The long-term pulmonary effects of chronic low-level lunar dust exposure have never been measured in humans because no human has experienced it. Animal studies and chemical analysis suggest it is a genuine health risk that requires engineering solutions like dust mitigation airlocks and air filtration systems to manage. The psychological challenges of long-duration isolation, confinement in small pressurized volumes, communication delays with Earth of up to a few seconds due to distance, and the profound psychological weight of being 250,000 miles from every other human being are areas where research is ongoing but incomplete. Medicine will learn what it cannot currently predict by doing. The first long-duration lunar missions will produce data that no simulation can provide. That is both the honest reality of the situation and the reason why medical systems for lunar bases must be built with significant capacity for treating conditions that weren't anticipated. Underneath all of these health challenges runs a simpler, structural fact about the Moon that governs its relationship with its own surface. The Moon has no magnetic field, and that absence shapes everything from radiation exposure to ancient atmospheric history in ways that reach back billions of years. Hold a compass anywhere on Earth, and the needle points toward the magnetic pole. Earth's magnetic field, generated by the churning motion of liquid iron in the planet's outer core, extends tens of thousands of miles into space. It deflects the solar wind, traps charged particles in radiation belts, and prevents the atmosphere from being slowly stripped away by the constant flow of particles from our star. The Moon has almost none of this. There is no global lunar magnetic field today. The Moon does have localized patches of magnetism in its crust, remnants frozen into ancient rock, but these are small, irregular, and incapable of providing the planet-wide shielding that Earth's field creates. Scientists believe the Moon once had a global magnetic field, generated by a liquid core in the first billion or so years of its existence. At some point, that core cooled sufficiently that the dynamo generating the field shut down, and the field collapsed. The consequences were gradual but permanent. Without a magnetic field, the Moon's early atmosphere, whatever thin envelope of gas volcanic activity produced in its first billion years, was exposed to the full force of the solar wind. Charged particles streaming outward from our star struck individual atmospheric molecules and gradually knocked them into space, a process called sputtering. Over hundreds of millions of years, whatever atmosphere the early Moon held was stripped away almost entirely. The Moon today retains only an exosphere, an extraordinarily thin scattering of atoms at the surface, so sparse it barely qualifies as a gas at all. The total mass of this exosphere is estimated at around 25 tons, roughly the weight of 2 large semi-trucks. Earth's atmosphere, for comparison, masses about 5 quadrillion tons. For astronauts, the absence of a magnetic field means direct exposure to the full radiation environment described earlier. But it also means that the lunar surface interacts directly with the solar wind in ways that have practical consequences. The helium-3 implantation, discussed in an earlier chapter, happens precisely because there is no magnetic barrier. The hydroxyl molecules detected in the lunar soil, a product of solar wind hydrogen combining with surface oxygen, also result from this direct exposure. The Moon's missing magnetic field is also a window into planetary science more broadly. Understanding exactly when the lunar dynamo shut down and why helps scientists model the magnetic evolution of other planetary bodies. Mars also lost its magnetic field early in its history, with similarly catastrophic consequences for its atmosphere. Venus appears to have never developed a strong dynamo field, despite being a similar size to Earth. The question of why Earth maintained its magnetic field while its neighbors did not is one of the central puzzles in planetary science, and the Moon, as the most accessible body for sample collection and seismic study, is a key part of answering it. The Moon's internal story, written in its missing field and its ancient rock, goes deeper still. One of the stranger confirmed facts about the Moon is that it is not geologically dead, and the evidence for that came from instruments that Apollo astronauts bolted to the ground over 50 years ago. The Moon looks still. From the surface it would appear static, ancient, frozen in the position it has held for billions of years. Every image we have of the lunar surface reinforces this impression. Grey rock, undisturbed dust, a world that stopped moving long ago. The seismometers that Apollo crews installed between 1969 and 1972 recorded something different. Over nearly a decade of operation, the Apollo passive seismic events, some were caused by meteorite impacts, easy to identify by their sharp, sudden signatures. Others were caused by the thermal expansion and contraction of the lunar crust as it moved from the extreme cold of lunar night into the heat of lunar day. But two categories of moonquakes proved genuinely mysterious and remain partially unexplained today. Shallow moonquakes occurred at depths of around 12 to 18 miles below the surface. They registered as high as magnitude 5.5 on a scale comparable to earthquake magnitude measurements. A magnitude 5.5 earthquake on Earth causes noticeable shaking and can damage poorly constructed buildings. On the Moon, these events produced something stranger. The seismic signals lasted for 10 to 20 minutes, far longer than comparable earthquakes, because the dry, cold, rigid lunar crust has almost no water or soft sediment to absorb seismic waves. The vibrations just kept bouncing. These shallow moonquakes are confirmed in the data, but their cause is disputed. Some researchers attribute them to ongoing tectonic activity driven by the slow cooling and contraction of the lunar interior. As the moon loses heat and shrinks slightly, the crust fractures. Recent analysis of images from the Lunar Reconnaissance Orbiter identified features called lobate scarps, essentially small cliffs formed by thrust faults distributed across the surface. These are confirmed as geologically young, meaning the moon is still contracting and still generating fault activity on its surface. Deep moonquakes occurred at depths of around 500 to 600 miles, near the base of the mantle. These happened with striking regularity, synchronized with the moon's orbital position relative to Earth. As the moon traces its elliptical orbit, Earth's gravitational pull varies slightly, squeezing and relaxing the deep interior in a tidal rhythm. This tidal forcing appears to trigger the deep moonquakes at predictable intervals. Scientists classify this as a well-supported explanation, though the exact mechanism at the source region is still being investigated. A third category, far rarer, produced signals suggesting large-scale slumping or movement of surface material, possibly from the rims of large craters. The Apollo network operated until 1977, when NASA shut it down for budget reasons. Decades later, researchers revisiting the archived data with modern analysis software found signals that the original hardware had recorded, but the processing technology of the time had failed to fully extract. The moon is still moving. It is still changing, slowly and subtly, but measurably. For engineers designing surface structures or lava tube habitats, this matters. A base expected to operate for decades must account for seismic activity. Pressurized habitats, power lines, drilling equipment, all of it must be engineered to tolerate occasional shaking from both the shallow and deep moonquake categories. And the moon's activity isn't limited to what happens below the surface. Its regolith, the loose fragmented soil covering the entire globe, may itself be a construction material that eliminates one of the most expensive logistical challenges facing any lunar base. Shipping a single pound of material from Earth to the lunar surface costs thousands of dollars using current launch technology. A pressurized habitat module, large enough to house 4 astronauts comfortably, with all required structural components, could weigh tens of thousands of pounds. The math of importing every building material from Earth produces mission costs that quickly become unsustainable for anything beyond a small temporary outpost. The moon's regolith may solve this problem. Lunar soil covers the entire surface to depths ranging from several yards to tens of yards depending on location. It is composed of fragmented rock, mineral grains and glass particles created by billions of years of micrometeorite impacts. It contains silicates, oxides and metals in proportions that engineers have studied extensively using Apollo samples and later analysis. Several research groups have demonstrated that this material can be directly processed into usable construction media without importing any binding agents or additives from Earth. The most studied approach is sintering. When regolith is heated to temperatures between roughly 1800 and 2000 degrees Fahrenheit, the glassy and mineral components partially melt and fuse together. The resulting material is rigid, load-bearing, and resistant to the thermal cycling of the lunar environment. Research groups, including a team at the European Space Agency, have demonstrated sintering using simulated lunar regolith and produced blocks with compressive strength comparable to standard construction concrete. A second approach uses sulfur as a binder. The moon's regolith contains sulfur-bearing minerals. At temperatures around 250 degrees Fahrenheit, sulfur melts into a liquid that bonds regolith particles together when cooled. Sulfur concrete sets quickly, does not require water, and performs well in a vacuum environment. Researchers at Louisiana State University demonstrated structural sulfur concrete using simulated lunar soil, confirming its viability as a local material application. Autonomous robotic construction using these materials is the critical enabling technology. A robotic system that mines regolith, processes it into building blocks, or extrudes it in layers, and assembles or prints structures according to a preloaded design, requires no human labor for the construction phase. Astronauts arrive at a habitat that robots built in the months before the crewed mission lands. Several companies have received funding from NASA's Small Business Innovation Research Program to develop regolith processing and construction robotics. The work is at varying stages of technology readiness, with some systems demonstrated at laboratory scale and others tested in simulated lunar environments at facilities like NASA's Marshall Space Flight Center. Landing pads are among the most immediately practical applications. Rocket exhaust striking loose regolith creates a sand-blasting effect that could damage nearby equipment. A sintered landing pad, produced by a robotic system before the first crewed lander arrives, significantly reduces this risk. The mass savings compared to shipping a landing pad from Earth are substantial. The longer-term vision, a base that continuously expands its pressurized volume using locally printed structures, is a more distant goal, but the first steps toward it are confirmed as technically feasible. A base that builds itself from its own ground is the engineering version of sustainability, and sustainability at a lunar base carries stakes that go beyond cost savings. In the event of a scenario where Earth itself faces a catastrophic threat, the Moon's self-sufficiency becomes something else entirely. The idea that humanity should establish a presence beyond Earth as insurance against extinction-level events on our home planet is sometimes dismissed as science fiction thinking. It is a serious, published scientific and philosophical position held by researchers across multiple disciplines. The threats are real and documented. A large asteroid impact of the kind that ended the Cretaceous period 66 million years ago represents a confirmed recurring risk category over geological timescales. The probability of a civilization-ending impact in any given century is very low, but across thousands of years, it is meaningful. No civilization has yet developed reliable planetary defense capable of diverting a large asteroid with limited warning time. Programs like NASA's Planetary Defense Coordination Office work on early detection and deflection strategies, and the Double Asteroid Redirection Test mission in 2022 confirmed that a kinetic impactor can alter an asteroid's orbit. Capability is improving, a gap still exists. Beyond impact risk, engineered biological threats, nuclear exchange, and rapid climate shifts each represent categories of risk that in worst-case scenarios could threaten the continuity of human civilization on Earth. A presence on the Moon, even a relatively small one, would be physically separated from every one of these threats simultaneously. A sufficiently developed moon base could serve as a repository for biological diversity, seed banks, genetic libraries, cultural archives, and the technical knowledge required to rebuild industrial civilization. This function requires a base capable of long-duration self-sufficiency, which brings together the water-ice resource, the lava tube shelter, the regolith construction technology, and the solar power infrastructure discussed in previous chapters. The Moon's proximity to Earth, which makes it the easiest target for early establishment, also makes it vulnerable in a specific scenario. A large enough impact on Earth will eject debris into space, some of which could strike the Moon. The Moon is close enough that it sits partly within the debris field of a major Earth catastrophe. For this reason, some researchers argue that true planetary redundancy requires a presence at Mars, significantly farther from Earth and completely outside any impact debris field. The Moon, in this framework, becomes the first step rather than the final destination. A civilization that can maintain a permanent outpost 240,000 miles from Earth has demonstrated the capability to extend further. A civilization that cannot maintain a permanent presence on the Moon will not successfully maintain one on Mars. Stephen Hawking, before his death, publicly advocated for off-world colonization as a survival imperative, stating that he believed humanity's long-term survival depended on spreading beyond Earth within the next century. This view is shared by researchers at institutions, including the Future of Humanity Institute at Oxford and the Centre for the Study of Existential Risk at Cambridge, both of which have published academic work on existential risk mitigation strategies that include space settlement. The moon as a backup isn't a fantasy, it is the early practical step toward an achievable goal. And the science happening on the moon, even before permanent habitation is established, reaches back into time in ways that shed light on the moon's own volatile past, including a period when the moon itself had something it no longer has today. The moon today has almost no atmosphere. The exosphere, that vanishingly thin scattering of atoms at the surface, would not register on any atmospheric pressure gauge built for Earth conditions. For all practical purposes, stand on the moon and you stand in a vacuum. Confirmed evidence from multiple sources suggests this was not always the case. Scientists analyzing the record of ancient volcanic activity on the moon have constructed a timeline of outgassing events, periods when volcanic eruptions released gases into space above the surface. The Luna Maria, the dark plains covering large portions of the near side, formed from vast eruptions of low-viscosity basaltic lava between roughly 3 billion and 1 billion years ago. Those eruptions were not silent. They released water vapor, carbon dioxide, sulfur dioxide, and other gases in quantities that at peak volcanic activity may have been significant enough to produce a thin but measurable atmosphere. A team of researchers published work in 2017 estimating that at the peak of lunar volcanic outgassing, roughly 3 to 4 billion years ago, the moon could have sustained an atmosphere with a surface pressure roughly 1.5% of Earth's current atmosphere, thinner than Mars has today, but physically real. This atmosphere would not have persisted long. Without a magnetic field to protect it from the solar wind, without sufficient gravity to hold lighter gases, and with no ongoing replenishment once volcanic activity declined, the atmosphere was lost to space over tens to hundreds of millions of years. The evidence for this ancient atmosphere sits in the regolith itself, certain volatile compounds that can only be deposited from an atmospheric source, including specific forms of water and sulfur-bearing minerals, have been detected in lunar samples at concentrations and distributions that are difficult to explain without an atmospheric transport mechanism. An atmosphere, even a thin one, would allow gas molecules to travel globally before settling to the surface, creating a more uniform distribution than direct cometary or asteroid delivery would produce. The mystery deepens with one specific question. If the moon had a thin atmosphere for tens of millions of years, and if that atmosphere contained water vapor, did any of that water condense and deposit in polar cold traps during that period? Some of the water ice at the South Pole today could have originated from the moon's own volcanic outgassing, rather than from external delivery by asteroids and comets. Separating these sources requires analyzing the chemical and isotopic composition of the ice itself. Different source materials leave different isotopic fingerprints. A mission that drills into the polar ice and returns stratified samples could read those layers as a chemical history, distinguishing between ancient volcanic water, asteroid-delivered water, and comet-delivered water by their signatures. That reading would tell scientists something remarkable. Whether the water available to future astronauts is partly the product of the moon's own geological past, a world that made some of its own resources and then lost everything else. The moon's history of loss extends beyond its atmosphere. It connects directly to Earth's story because the moon's gravitational presence has been silently governing one of the most fundamental aspects of life's existence on our planet for billions of years. Remove the moon from Earth's orbit and run the simulation forward. The results are deeply unsettling. Earth's axial tilt, currently around 23.5 degrees, is what gives us seasons. The northern hemisphere leans toward our star in June and away from it in December. This tilt is stable over human timescales, varying only slightly over cycles of tens of thousands of years, in a predictable pattern called Milankovitch cycles that scientists have confirmed are tied to ice ages throughout Earth's history. The moon stabilizes this tilt. Its gravitational influence acts as a damper on the precession and wobble of Earth's rotational axis, keeping the tilt within a relatively narrow range over geological timescales. Without the moon, Computer simulations run by researchers at the Observatoire de Paris and other institutions show that Earth's axial tilt could vary chaotically, potentially swinging from near 0 degrees, essentially no seasons with permanent tropical conditions at the equator, and permanent ice at the poles, to over 80 degrees, a nearly sideways tilt, where polar regions would bake in continuous sunlight for months and then plunge into darkness, with the entire climate system lurching between extremes on geological timescales. These simulations are modeling exercises, not confirmed predictions, because the chaotic nature of the scenario makes precise outcomes impossible to calculate. But the underlying gravitational physics is confirmed, and the range of possible tilts without lunar stabilization is a settled scientific inference. A climate system varying chaotically in its axial tilt would face dramatically altered growing seasons, radically different precipitation patterns, and potential ice ages and heat pulses of a severity far beyond what Earth has experienced in the past several 100 million years. Whether complex life as we know it could have evolved or continued to thrive under those conditions is a genuine, open question. The Moon's mass and orbital position provide a stabilizing influence that may have been a prerequisite for the kind of stable, long-duration climate that allowed complex ecosystems to develop on Earth. This places the Moon in a category that goes far beyond a nearby geological body. It is possibly a structural requirement for the kind of biosphere we inhabit. This connection between the Moon's presence and Earth's habitability adds a dimension to the case for understanding and preserving the Moon's environment that goes beyond resource extraction. Whatever is done on the Moon over the coming decades will be done in the neighborhood of the body that helped make Earth livable. The Moon holds still another surprise in store for anyone looking at the deep sky. Its far side, shielded from Earth's radio noise, could open a window onto the universe's earliest light, a signal so faint that no instrument built on Earth has yet succeeded in cleanly detecting it. Before the first star ignited, the universe was dark. For hundreds of millions of years after the Big Bang, space was filled with a fog of hydrogen gas. No light, no stars, no galaxies. Just atoms slowly drifting, gradually being pulled together by gravity into the first structures that would eventually become stars. Scientists call this era the Cosmic Dark Ages, and it represents the largest gap in our observational knowledge of the universe's history. The physics of this era is understood in outline. The details, how exactly the first stars formed, what triggered the end of the Dark Ages, whether the process happened uniformly or in patches, are almost entirely unknown through direct observation. The reason is simple. The primary record of this era is encoded in radio waves. Specifically, in the 21 centimeter line, a radio emission produced by neutral hydrogen atoms at a specific wavelength. These signals, emitted by the hydrogen fog of the early universe, have been stretched by the expansion of the universe as they traveled to us across over 13 billion years. They arrive today at much longer wavelengths, in the very low frequency radio band. Detecting them requires a receiver that can hear them against the background of all other radio noise in the universe. And on Earth, that task is nearly impossible. The ionosphere absorbs and distorts low-frequency signals from space. Human technology generates interference at exactly the frequencies where these ancient signals sit. The noise floor on Earth, even in the most remote radio-quiet zones, buries the signal we are trying to hear. The far side of the Moon eliminates every one of these obstacles simultaneously. The Moon's own bulk shields the far side from every radio signal Earth generates. The Moon has no ionosphere. The far side surface, in radio terms, is the quietest location in the inner solar system that humans can practically reach. An array of radio antennas deployed across the far side, each one simple in design but linked together in a network spanning miles, could synthesize the sensitivity of a telescope far larger than any physical dish ever built. The technology for this kind of distributed array exists on Earth, used by radio telescope networks that link antennas across continents. Placing a version of it on the far side of the Moon would give astronomers access to frequency ranges never before observed, cleanly. The science targets go beyond the 21 centimeter signal. Plasma emissions from exoplanets with magnetic fields produce low-frequency radio signals that might be detectable from the far side, giving scientists a new method for identifying and characterizing planets around other stars. Solar bursts, the outward shock waves from coronal mass ejections, produce radio signatures at these frequencies that could improve space weather forecasting for Earth and future deep space missions. The proposed Lunar Farside Explorer mission and the Dark Ages Polarimetry Pathfinder concept are among several ideas in varying stages of planning and proposal. None has yet been funded and approved for flight as of 2024, but the scientific community's interest is strong, and the concept's feasibility has been confirmed in multiple technical studies. A telescope on the far side of the Moon could hear the universe speak in frequencies it has never been able to transmit cleanly to any human instrument. The words it is carrying are from before stars existed. What that first chapter of cosmic history says could reshape our understanding of everything that came after. And there is one more frontier that the Moon unlocks, one whose scale of ambition makes every other chapter in this story look modest. It involves rocks flying through space, trillions of dollars in raw materials, and a plan to turn the Moon into the operational headquarters for a solar system-wide mining economy. The asteroids closest to Earth contain resources that dwarf anything on the lunar surface. A single metallic asteroid, roughly half a mile across, can contain more iron, nickel, cobalt, platinum, and rare metals than humanity has extracted from Earth in all of recorded history. The asteroid 16 Psyche, orbiting in the main asteroid belt, is estimated by NASA scientists to contain metal resources valued at a figure so large it is effectively meaningless as a dollar amount in current economic terms, somewhere in the range of $10 quintillion at current commodity prices, a number that exceeds the entire current global economy by a factor of roughly 1 million. Most near-Earth asteroids are far smaller, but many still contain resources of significant practical value. Platinum group metals, including platinum, palladium, and iridium, are critical for fuel cells, catalytic converters, and electronics, and their Earth supply is geologically limited. Several near-Earth asteroids, confirmed through spectroscopic observation, contain platinum group metal signatures. The challenge of asteroid mining has always been the economics of getting there, extracting the material, and returning it or processing it in space. Missions from Earth to near-Earth asteroids require significant propellant, and the return trip requires either landing the extracted material on Earth, with all the heat shield and atmospheric entry challenges that involves, or processing it in space for in-space use. The Moon changes this calculation. A propellant depot at the Moon, fueled by ice from the South Pole, dramatically reduces the cost of a round trip to a near-Earth asteroid. A spacecraft that launches from lunar orbit rather than Earth orbit starts its journey with a substantial gravitational advantage. It needs less fuel to reach the asteroid and, critically, can afford to carry more cargo home. For asteroids whose ore would be used in space rather than returned to Earth, the Moon becomes a processing and manufacturing hub. Raw ore brought from an asteroid to a lunar facility could be smelted, refined, and formed into components used for construction of further space infrastructure. Structural elements for gateway expansions, radiation shielding material for deep space vessels, components for future Mars mission hardware, all potentially manufactured from asteroid-sourced metal at a lunar facility rather than shipped from Earth. Several private companies formed in the 2010s with asteroid mining as their stated business model have since pivoted or dissolved as the timeline for economic viability stretched further than their initial capital could sustain. The technical feasibility is not in doubt. The economic feasibility requires a cost of space access, and specifically a cost of propellant in space. That does not yet exist. Lunar propellant production is the economic unlock. When that exists, and mission planners in multiple agencies believe it will exist in some form by the 2030s or 2040s, the asteroid mining equation changes fundamentally. The Moon as the hub of a solar system economy is not a concept being discussed only in speculative circles. It appears in official long-range planning documents from NASA, the European Space Agency, and in academic space economics literature. The timeline is long, the physics is sound, the infrastructure required is the hard part. And that infrastructure, built on the Moon and in lunar orbit, also serves another purpose that has nothing to do with economics and everything to do with understanding where we came from and possibly where other life might be. Every crater on the Moon's surface is a timestamp. The Moon's geology, preserves the record of asteroid and comet impacts across the entire history of the inner solar system. Because the Moon lacks the geological resurfacing processes that erase craters on Earth, its surface retains impacts from as far back as 4 billion years ago, sitting alongside much more recent ones. The density of craters in a given region tells scientists how old that surface is. The size and distribution of craters reveals the population of impacting bodies that were circulating through the solar system at different times. This record, called the lunar cratering chronology, is the primary tool scientists use to date the surfaces of other solar system bodies. A region on Mars, Mercury, or an asteroid is dated by comparing its crater density to equivalent regions on the Moon, whose ages have been independently confirmed by isotopic analysis of Apollo samples. The catch is that the Apollo samples were collected from a limited number of locations on the near side, clustering the data in ways that leave significant gaps. The chronology derived from them is solid for the last 3 billion years, but increasingly uncertain as it extends further back in time toward the period of the late heavy bombardment and the very early solar system. Sample return missions targeting ancient regions of the Moon, specifically parts of the South Pole Aitken Basin and the heavily cratered southern highlands, would provide calibration points at ages that Apollo did not reach. With those additional data points, scientists could sharpen the entire chronological framework used to date surfaces across the solar system. Here is the broader implication. Dating surfaces precisely allows scientists to reconstruct the history of impact rates in the inner solar system. If the impact rate was high during a specific window in the past, that tells us something about what was happening in the outer solar system at that time. Possibly massive planetary migrations that destabilized the asteroid belt. If the rate declined at a specific date, that defines when conditions became stable enough for life to persist on Earth without constant catastrophic disruption. The Moon's craters are a clock that measures the history of the entire neighborhood. Planetary scientists are building a wish list for future lunar sample return, targeting locations that span the widest possible range of ages and geological origins. The ambition is to resolve questions that have been open since the Apollo era. Questions about the solar system's dynamical history that no amount of remote sensing can answer without physical samples in hand. The Moon as a time capsule holds 50 years of unfinished business from Apollo. The next wave of missions, human and robotic, will finish reading it. And what that reading tells us about the probability of life elsewhere in the universe connects the Moon's scientific role to its most profound implication. The same conditions that allowed life on Earth, the stable tilt, the water delivery, the impact history, may or may not exist around other stars. Knowing how precisely those conditions had to be met here is essential for understanding whether we are alone. The question of whether life exists elsewhere in the universe is the largest open question in science. The Moon is not where the answer will be found, but it is where several of the inputs to that answer will be sharpened. The search for life beyond Earth rests on understanding how life arose here. That understanding, as discussed earlier, depends on knowing the conditions of early Earth with precision. The impact history, the water delivery rate, the timing of stable conditions. The Moon is the key to most of those measurements. Beyond Earth's own history, the Moon enables the far-side radio telescope concept that could detect signatures from exoplanets at frequencies currently inaccessible from Earth. Magnetic field signatures from large exoplanets, detectable at very low frequencies, could help identify worlds with the kind of magnetic protection that may be important for long-duration habitability. But the Moon connects to the broader question of life in a more philosophical way as well. The conditions that produced Earth's Moon appear to require a specific sequence of events. The leading confirmed scientific theory for the Moon's formation is the giant impact hypothesis. A Mars-sized body struck the early Earth, roughly 4.5 billion years ago, at an angle and velocity that ejected a massive cloud of material into orbit, which then coalesced into the Moon. This event was energetically extraordinary. It nearly destroyed both bodies. It produced a Moon of exactly the mass and orbital distance needed to stabilize Earth's tilt and drive tidal rhythms that may have influenced the chemistry of early life in tidal pools. The probability of this specific impact, at the right angle, with the right body, at the right time in Earth's development, is difficult to calculate and actively debated among planetary scientists. What is not debated is that the outcome was unusual. Of the rocky planets in our solar system, only Earth has a large moon relative to its own size. Mars has 2 tiny captured asteroids. Venus and Mercury have none. If a large, stabilizing moon is a prerequisite for the kind of long-duration, stable biosphere that produces complex life, then the rarity of systems with such moons becomes part of the calculation for how common complex life might be in the galaxy. The rare Earth hypothesis, proposed by paleontologist Peter Ward and astronomer Joe Kirschvink, argues that the combination of factors producing complex life on Earth are collectively so unlikely that complex life may be extraordinarily rare in the universe. Even if simple microbial life is widespread, the moon sits near the center of that argument. Its existence may be one of the conditions that made us possible. Its study continues to refine how unique or how common those conditions are. Every measurement taken on the moon, every sample returned, every crater dated, every ice core extracted, adds precision to the most important calculation humanity has ever attempted: whether the universe made us once or many times. The final question is the one that determines whether any of this reaches its potential. The legal and ownership framework governing the moon will either allow this science and this development to proceed cooperatively, or it will fragment it into a geopolitical competition that serves no one's best interests. The next century of human presence in space may be decided not by rocket engineers, but by lawyers, diplomats, and the governments that deploy them. The Outer Space Treaty of 1967 is the foundational document of international space law. It has been ratified by over 100 nations. Its core principle is clear: no nation can claim sovereignty over the moon or any other celestial body. The moon belongs to humanity as a whole, in the language of the treaty, the province of all mankind. That principle has never been seriously tested, because until now, no nation had the practical capacity to establish a permanent extractive presence on the moon. The treaty was negotiated between the United States and the Soviet Union at the height of the space race, when landing a human on the moon at all was the ambition. Resource extraction was a distant hypothetical. The hypothetical is becoming real. The Moon Agreement of 1979 attempted to go further than the Outer Space Treaty, establishing the moon and its resources as the common heritage of mankind, and requiring that any exploitation be governed by an international regime yet to be created. The Moon Agreement has been ratified by only 18 nations. The United States, Russia, China, the European Space Agency member states, Japan, and India have not ratified it. It is effectively non-binding for every nation with an active space program. The current legal situation can be summarized this way: the moon cannot be owned by any nation, but the resources extracted from it may be owned by whoever extracts them, under the interpretation adopted by the United States and reflected in the Artemis Accords. This interpretation is disputed by nations that believe resource extraction requires prior international agreement. Into this gap, private actors are moving. Several American companies have received licenses from the Federal Aviation Administration and the Department of Transportation to conduct commercial lunar operations. The licensing framework treats commercial lunar activity as an extension of national activity, which the Outer Space Treaty permits nations to authorize and supervise. A private company licensed by the United States government to operate on the moon is, in legal terms, operating under American supervision without making an American territorial claim. Whether this distinction holds under international scrutiny when a private company begins large-scale water ice extraction from a permanently shadowed crater is untested. No court with clear jurisdiction over such a dispute exists. The International Court of Justice can only adjudicate disputes between nations that consent to its jurisdiction. Disputes involving private commercial entities in international space fall into a legal vacuum that current treaties do not address. Legal scholars at institutions including the University of Nebraska Space Law Program and the European Space Policy Institute have published extensively on this gap. The consensus is that the current framework is inadequate for the commercial era of space development, and that either a new treaty or a set of binding international guidelines is required before large-scale lunar operations begin. The diplomatic timeline for negotiating such a framework is measured in years to decades. The engineering timeline for establishing permanent lunar operations is measured in years. The two timelines are not synchronized, and the engineering timeline is currently moving faster. What gets built on the moon before international law catches up will be very difficult to undo. The legal framework that governs humanity's relationship with the moon and the resources it holds may ultimately be written not in negotiating rooms, but by whatever is already on the ground when the lawyers arrive. The stakes could not be higher, and the people who will live and work inside those first permanent outposts will experience the moon not as a destination but as a home, with all the challenges and discoveries it entails. The next humans to walk on the moon will not stay for 3 days. Artemis mission planning and the broader architecture of what comes after it envisions surface stays that grow progressively longer. Early Artemis crewed landings target stays of roughly a week. Subsequent missions, as the base infrastructure develops, are expected to extend to 30 days. The long-term goal is rotational crews remaining at a South Pole base for months at a time, with one crew arriving as another departs. That shift from days to months is the difference between visiting and inhabiting. The experience of being on the moon for months will be unlike anything in human history. From the surface, Earth hangs in the sky, visibly rotating, passing through phases the way the moon does from Earth, but 4 times larger in apparent size and enormously brighter. It does not rise or set. It stays fixed in the sky from any given point on the lunar surface, a consequence of the moon's synchronous rotation with Earth. For an astronaut working a surface shift, Earth is always there, brilliant and blue, hanging motionless overhead. The day-night cycle at a South Pole base, positioned on a peak of near-eternal light, would be nearly continuous illumination, broken only by brief periods of dimming as the geometry of the orbit shifts. Biologically, this presents challenges. Human circadian rhythms evolved for a 24-hour cycle, with clear light-dark alternation. Living under near-continuous light requires deliberate scheduling of sleep environments, light-blocking systems in habitats, and careful management of sleep timing. The effects of long-duration exposure to this environment on human psychological health are an active research area. Communication with Earth is delayed by roughly 1.25 seconds each way, a round trip of about 2.5 seconds. That lag is small enough to allow near real-time conversation, unlike the minutes-long delays of a Mars mission. Astronauts on the moon could make video calls to family and colleagues on Earth with only a slight delay. This psychological connection to home is considered significant by space medicine researchers who study isolation and confinement. The people who live there for months will develop an intimacy with the lunar environment that brief visits cannot produce. They will know specific boulders by position, track changes in dust distribution after rocket arrivals and departures, observe the slow movement of Earth's phases across the sky through weeks of observation. They will experience the full weight of being somewhere else entirely, separated from every other human being by 250,000 miles of vacuum. They will also do science, maintained geological survey of the South Pole region, seismic monitoring from a new network of instruments, long baseline astronomical observation, continuous monitoring of the ice extraction and processing systems, medical self-monitoring that will generate the first real data on long-duration human health in lunar gravity. They will fix things that break. They will adapt plans when conditions differ from simulations. They will encounter problems that no mission planner anticipated, because no one has been there long enough before to know what those problems are. Each crew rotation will carry back knowledge that the next crew uses to stay a little longer, go a little further, and build a little more. The moon is not the final destination. The people who inhabit it will know that clearly. They are building the first rung of a ladder. Below them, Earth hangs blue and luminous in the lunar sky. Above them, the rest of the solar system waits. They will be the first humans for whom leaving Earth is something that happened in the past. For them, the moon is simply where they live, and from where they stand, everything beyond it has just become reachable.